Let's go to Remi then. So I'm gonna put it back on mute. Remi, would you like to go ahead, sir? He just disappeared. On there he is.
Once again, I'd like to thank Daniel Sheehan. Came at a very important point in my life when I was doing my PhD. My friend linked me up with Daniel, and his publications with APEC and others confirmed what I've been thinking for a number of years. Okay, I initially started out just working in an engineering inventor mindset, looking at water desalination, and the problem started looking at figures of merit, and that got me awfully suspicious, and then one thing led to another. Can also say as well, as you do new science, this is why what I was trying to say to Steve originally, why do we believe the things that we believe? If you have an understanding, and it doesn't have to be in a super high technical level, physics review level, but if you have some mechanism, some belief, you can communicate it to others and you can get others to join you. Because you need to get rid of nebulous thinking and start dealing in concrete principles, yes? Because in the real world, you have to interface with a conservative establishment. You have to link with people who are enthralled to this conservative establishment, so investors, venture capitalists. So it's very important to be able to say why you believe the things you believe, and if you can quantify it, if you can mathematize it somehow. And it doesn't mean necessarily you'll find engineers and physicists, there's a blurring of lines. Okay, so I'm going to move on to my presentation. I better share the screen. Done it again, not thinking ahead. Share the screen. Let's move this over here. And let's go here. Sure. Are you seeing my second screen? Are you seeing APEC Conference's second law challenges? Are you seeing that? Hello?
Yes, I'm sorry about that. Yeah.
Yeah, good. Okay, you have to excuse me. I've been off this for about 5 years. I attended the same conference as Daniel set up. I have a paper and a slide. They're in kind of reverse order to one another. The slideshow is more concerned with cutting to the chase of how I would go about things. The paper, which I intended for AAAS, and really just through my own sort of lack of tenacity, I didn't push through enough to get into the proceedings, deals with more the why of things, and then it gets onto how I might do something. So if I walk you through the paper, what I'm trying to do, I'm trying to find a principle behind all of this. So I'm talking about heat engines of extraordinary efficiency. And I believe there's a sliding scale from Carnot to Maxwell Demon or Maxwell Zombie engines, as Daniel Sheehan calls them. Now, bear with me, I've been off this some time. Let me cut to the chase with what I'm saying here with this figure 1. So on the left-hand side, let's look at the axes. The y-axis is not doing anything. It's really the x-axis is just showing the efficiency. And I'm categorizing things as I move from left to right. So on the left-hand side, we have the Carnot engine. So you're condemned, it seems, to waste a certain amount of heat to get a smidgen of work out. It, as they believe, represents the absolute maximum you can extract from turning heat into work. Now, I believe, and this is what Daniel's getting at, it's just inconsistency around this whole second law thing. Because what is a heat engine? Well, it's some Victorian or earlier notion that you've got a furnace and you burn some coal or whatever, and you've got some steam cycle, and then you've got a reservoir to cool your working fluid. Well, no, that's not correct. Anything that generates entropy as an intrinsic part of its operation is a heat engine. Let's be correct in that, right? So before I go on, I'll just say what this concept of entropy is. Okay, you multiply a change in entropy. Entropy is the randomness associated with a system. Heat energy is just random, essentially random kinetic energy. It can be other forms of energy, but it's energy that's become randomized. You start out with high grade sources of energy, so say a hydroelectric plant with the reservoir on top of a mountain. By the time it gets down to the bottom, you want to convert it into electrical energy. If you didn't do that, it would just go into turbulence. The high grade form of energy, which is the potential energy of the water, would just end up as heat in the water from all the turbulence. So what entropy is saying, the concept invented by Clausius, and the technical manifestation of this is to say he introduced an integrating factor in the thermodynamic intensity. That's all the technical garb about it. But what it amounts to is saying that systems become randomized over time. Yes, and it seems inevitable. The classic example, take a card pack and shuffle it, distribute cards. You're not going to see all the suites in order. It's highly unlikely. So this is the limiting belief of the establishment as regards to energy transmutations. High-grade energy degrades into low-grade energy, and then you reach thermal equilibrium where, because you're at thermodynamic equilibrium, essentially everything's grey. You have no difference from one area to another. You can't run a heat engine. If you run a heat engine, you want a difference in something. So if you have a piston, you have high pressure push into a low pressure environment. You can extract work that way. When you approach thermodynamic equilibrium, which is the state of maximum entropy, that's it. According to the current thinking, nothing more you can do. So let's get back to this diagram. What I said on the left-hand side with conventional Carnot thinking, well, I consider fuel cells and biological systems as heat engines too, because they generate heat, they make waste heat. There's an increase in entropy, but they're much more efficient than Carnot engines. If you look at fuel cells, they're 80% efficient. So that ought to get people thinking. If you extend the definition of a heat engine and bring in more cases of things which are generated entropy intrinsically, well, they're superseded Carnot efficiency. If you look at biological systems, and if you look at, say, the writings of E.T. James, you'll probably find a reference in this paper. It's on my usual, you can go to my website, you can go to academia.edu and you'll find this paper. E.T. James said that for the human body to do what it does, for muscles to do what it does, you'd be operating at 6,000 Kelvin. So obviously the body is operating at a much higher efficiency. It's doing things that conventional thermodynamics says that you can't. So we start to move over to the right sector. So if we look at the middle diagram, so we've shown a flow of heat energy in, is work out, and some heat energy going to the environment. It's better than the left-hand case. The efficiency is higher. So we define the efficiency as the work out divided by the amount of heat put in. We go to the right sector and start heading towards over unity. What we've done here is that if you look, the arrow's in the reverse direction. Instead of rejecting heat to the environment, you're taking heat from the environment and converting it into work, converting it back into high grade energy. So the efficiency could go off to infinity. Okay, so that's what I call the continuum of heat engines. Now, reiterating what Dan has said about this ought to be telling people, they should be getting suspicious now, but the thing is so nebulously defined that there's got to be loopholes. If you look at, say, just 3 definitions of the second law that Dan has brought out, the Carnot theorem, saying that there's no engine that can operate between two reservoirs at greater efficiency than the Carnot engine. That's a statement of the second law, or is that the Kelvin Planck? Sorry, I haven't done this for a number of years. Kelvin Planck, no device operating in a cycle can produce the sole effect of the extraction of a quantity of heat from a reservoir and the performance of an equal quantity of work. Then you've got the Clapeyron's definition. No process is possible for which the sole effect is that heat flows from a reservoir at a given temperature to a reservoir at a higher temperature. On that particular point, what got me going on that some time ago was a rather wise old physical chemist at one of the London University colleges. And he got me thinking. He said, Remi, did you know about steam injectors in the old locomotives? He said, heat flows uphill. Did you know that? And the reason why is when you re-inject the heat, the steam back into the boiler, it's a constant temperature process from the latent heat, and heat energy is able to flow uphill, even though the boiler may be, say, at 120 degrees centigrade. That's just an aside. That's one of the early things that got me thinking about this. So I'm looking for the general principle behind how you can have heat engines of extraordinary efficiency. I mean, what is going on? What's my thinking? And how does my thinking lead me on to physical devices? Let's take thermodynamic equilibrium and fluctuations. At thermodynamic equilibrium, everything is not settled. Obviously, you have these random movements of atoms and molecules, and these fluctuations. If you consider things like this in a quirky way of two systems, so one system is momentarily hotter than an adjacent system, yes? It can transfer heat energy and do work on the other system at 0 temperature, and vice versa. So if you were to consider a gas and all the fluctuation going on and break those down into little subsystems, you've got all this transfer of heat and work going on, yes, at 0 degrees Celsius, sorry, at a 0 temperature difference, or tending to zero temperature difference, right? So this led me to believe that you can have a constant temperature microscopic work theorem. At constant temperature, microscopic heat and work are available, and they can partition across the phase boundary. So if I move on to my next idea, if you have a phase, what is a phase? A phase of a material is something with defined chemical and physical properties. So you could say have water, ice. So ice would be in one phase and water would be in the other, and the ice is melting or in equilibrium with the water at 0 degrees centigrade. So you've got one aspect of the system which is macroscopic, two aspects, the liquid and the solid. And they would be called different phases. So this is all hinting to me that there's some underlying principle going on why you can perhaps build macroscopic heat engines. And we're not talking about now just the microscopic aspects of heat engines where you've got this continual flow in thermodynamic fluctuation of heat being turned into work and back and forth again. Can you do that macroscopically? And this is what dawned on me as the sort of general principle. So first, I'll just run you through the limiting belief of the Carnot cycle. It's the usual thing on the PV diagram or temperature entropy diagram. You've got adiabatics, the steeper lines, alternating with isothermals. And the idea is that by, say, having a gas, your working fluid it's called, operating between two reservoirs, a hot and a cold, you can get it to go through a sequence of expansion and contraction to get it to perform that work. So you do alternating isothermals with adiabatics. The adiabatics are steeper. Yes, adiabatics are what they call an isentropic process. There's no heat flow. So typically what you do, you take your gas, you put it in contact with the hot reservoir, it expands, do work from that. And then, so it expands on 2 and 3, the section 2 and 3. It's an isentropic process, there's no flow of heat because you've taken it away from the reservoir. And then to complete your cycle, you put it in contact with the lower reservoir to reject heat. And then that will cause it to contract and you can go around your cycle again. The area would be the work. On a temperature entropy diagram, it's a similar concept. You can see that the isothermals, just checking my diagram here, the adiabatics, I think I've got my numbers out of sync here. But anyway, the isothermals would be the vertical parts. The adiabatics, sorry, got it round the wrong way, sorry. The isothermals would incur changes in entropy. There's a flow of heat. The adiabatics are the vertical segments. And once again, the area is the work. The two diagrams are synonymous. So I got to thinking, what it comes down to, you want to carve out an area in PV space or temperature entropy space. So what would happen if you just had one substance? You could only really just go up and down one line. It's either an isothermal or an adiabatic. You can't carve out an area. And the way around this, if you could somehow jump off these isothermals and these adiabatics by getting the material to behave almost like a different material, you would carve out this area. And it dawned on me that was a phase change. Yes? So when you start looking at things, you're thinking, what is special about phase changes? How are they able to somehow gather microscopic work and turn it into macroscopic work? Well, I remember this from my old school days, you know, the chemistry master or the physics master. They're talking about evaporation. Take a first order phase transition, ice to water, water to steam. You know, when you draw the Maxwell-Boltzmann distribution, you have an energy barrier. So what happens, you don't just have the molecules and the atoms at one set temperature, they have a statistical spread given by the Boltzmann function. So when you're dealing with things like evaporation, you're finding that the more energetic members are surmounting this energy barrier, and then they're going into the higher phase. Well, that looks like a sorting process to me. Yeah. Something's happened. So I just heard a bleep. Yeah. So that's the sorting process. That's the first order. Now, there are things called second order transitions, which are more gradual. They're called order disorder transitions. I'll give an example. One of those is with just a common or garden India rubber band. You can do this if you can find one of those sort of pretty lush rubber bands that say the postman wraps your mail in. Yes, if you put it to your lips, and then if you expand it suddenly, you'll find it warms up. And the reason why is you're freezing out degrees of freedom. So you remember, heat energy is a partition of microscopic random motion, kinetic and potential energy. It's random motion. So when you have these rubber molecules inside this rubber band, when you pull it taut, you're stopping these rubber molecules from vibrating. You're freezing out a degree of freedom. So the energy repartitions to the rest of the system. That's why you find that the rubber band has gone up in temperature. So this is a gradual process. You can stretch the band gradually. It's an order disorder transition. So initially, I started out looking at first order systems. I'm going to jump towards the end of the paper and show you what I initially considered. The device I called the phase changing catalyst. The idea was to put inside a closed isolated system, and that's an interesting point, a closed isolated system, to put a device where you have a reservoir of water and above it water vapor. The idea was to have a column full of a hygroscopic material which will condense the water vapor and build up sufficient head so that pure water would come out the bottom from a reverse osmosis membrane. Not too practical. I looked into this. You might need a column 3 kilometers high, and you do all the sums and you can work it out. But what you've got there, as Daniel was saying, you've got macroscopic perpetual motion. Let me just say there's no such thing as perpetual motion. Let me say that if the universe has an ending point, even for heat energy, which is microscopic, so-called perpetual motion, it has to end. This device, although it will show a macroscopic flow, would fail at some point. The membrane would get fouled up. It would fail at some point, but in its operation, it has converted heat energy into useful work. So you've recycled heat energy. Okay, so let's just have a quick look at the basis of this. The water vapor would exist in equilibrium. So it's an equilibrium system. Equilibrium systems are not meant to be able to do any work in an equilibrium system for the reason I told you, that essentially everything is grey. You want a piston to have a pressure difference, or a thermocouple, you want a temperature difference. So it's an equilibrium system on the whole. What's happening is that the water vapor, as you go up, obviously you've got a barometric fall in pressure, but it's still enough to be condensed by the hygroscopic fluid. It then flows downwards and exits at the bottom as liquid water. But in doing so, in condensing, you're also getting temperature difference. You're getting the latent heat effect. And one can do the sums in this first law, second law. And this is my very early considerations on this. It's not practical, yes. So my thoughts turn to a magnetic system, second order phase transition, order disorder transition. And the idea was to use something like the magnetocalorific effect or temporary remnants from a ferrofluid. It's a bit subtle to go into without reading all the papers, and I don't think I could distill across in this presentation at the sort of general level the slight differences between the two systems, a magnetocalorific effect and the temporary remnants. So I'm going to dwell on the temporary remnants cycle because it's just the most intuitively obvious. So if you've ever come across ferrofluid, it's essentially a fine suspension, extremely fine colloidal suspension of magnetic particles in a liquid. Now they're so small, they're undergoing Brownian motion. Now, the thing about it is that you can magnetize it, and you can magnetize it in such a way that it doesn't suffer hysteresis loss. If you turn the magnetic field on slowly, it won't heat up, yes? When you take the field off, suddenly the dipoles will be randomized by the thermal motion, yes? And I was thinking, isn't that a system of turning directly heat energy into electrical energy? So there's a few technicalities involved, but it's as simple as that. And as Daniel was saying, these devices don't have to be conceptually difficult. The difficult thing is convincing people who don't want to believe, as I found my PhD supervisors, one of them. So here's what I was proposing. I built a model. I essentially, because I wasn't having this support from my supervisors. I essentially ran out of money to develop this. It was going to take about half a million pounds to develop the ferrofluid to my specifications. A lovely chap, Professor O'Grady at Bangor and the University of York. Lovely chap. He was in charge of a company called Liquids Research, and he told me that's the kind of input you would need to develop the ferrofluid to specification. But anyway, so what I did, I just developed a kinetic theory model where essentially I just set up a computer program and showed dipoles, magnetic dipoles interacting with each other, and show that the model could thermally randomize, i.e. reach equilibrium. I mean, I showed a relaxation effect. When you put the field on, the dipoles would line up, take the field off, and then they'd re-randomized. And so it was easy to then just get the MATLAB script to just give me temperature and entropy, and I could prove my point, at least with a computer simulation. Okay. I think this is all a bit too technical. You can't really, you have to read it line by line. Yeah. So I'm going to switch now to the other slideshow. The slideshow, which I prepared for that conference, where I really started in reverse order. So I just wanted to share a few slides with you from the slideshow, where I was linking in with what Daniel Sheehan was saying, with his idea that you don't just want to bring unnecessary, you don't want to have unnecessary fuel supplies if you can use the heat energy in a sensible manner on your spaceship. Yes? So this ought to not be possible. Can you maximize the slides? Fair enough. Let's go F5 on that. And let's share the other screen. Bear with me. Let me share. Okay. I'm just going to fast forward on the slideshow to where I was. See, the early part of the slide is more concerned with the how, and I just wanted to get on, the latter part was concerned more with the why. Okay, so this is what Daniel Sheehan was getting at, which apparently is impossible at the current readings of the second law. You can have a reservoir which is just storing masses of heat, and you can have your Maxwell zombie reconstitution that heat energy and turn it into useful work, which eventually becomes friction again and just goes around the cycle. That ought to not be possible, but it is. Okay, so I think really without too much present preparation and adequate refactoring of the slides, I'd probably call it to a close there. But I just wanted to say there's a why behind all this. It's the sorting of molecular entities by an unintelligent sorting process. This whole idea of the Maxwell demon was that you require something with, if not intelligence, it would at least need to know the state of things. You'd need to have some kind of state engine to say, I've opened the gate, I've let a fast one go through, I close the gate when I see a slow one. And according to Szilard and Shimalski, that process of storing that information would require rejection of heat energy into the environment, and you wouldn't get more out than you put in. And that's sort of spurred the whole field of information theory and the idea of reversible computing. I wanted to sort of link into those areas, but I think it's probably going to be a little bit too technical, a little bit overwhelming. But the key point, the key take-home point is that you have demon zombie processes. They don't need to be intelligent. They don't need to store state information. It's all implicit in their work. It's all implicit in the molecular dynamics of things, and these things can occur. Now, my particular subset was looking at phase changes, because I struck on this idea that if you can partition microscopic work, which an infinite amount can happen at zero temperature difference, if you can partition it between two phases and make one phase unstable, you can then liberate work macroscopically. There are other ways, as Daniel has said, maybe things like thermal rectifiers and so forth. Okay, there's some take-home messages. You've got the whole take-home messages. The idea that you can get, there's always microscopic work going on. There's a continual interchange of microscopic heat flows, microscopic work. You can get that to partition across a phase boundary. A phase is a macroscopic manifestation of microscopic properties. So you're going from the microscopic to the macroscopic. You then make your phase unstable, and you get that microscopic work turned into macroscopic work. That's essentially the take-home message. And it is a sorting process. It is a Maxwell zombie, as Daniel has been saying for years. And these things are possible. It's not the only way of doing it. There are lots of ways of doing it. And Daniel has said, essentially, these things are simple and they can be done. Now, I may return to this with the ferrofluids if I raise new funding. At the moment, I'm probably working on too many things at the moment. Okay, so I'll hand over, and yeah, that's my segment. Okay.
Oh, okay. So let's do this then. And Remi, thank you. I want to put it on speaker. Everyone, please give Remi an enormous hand.